Hey guys, welcome back to chapter 14. This will be the last skill that you guys will learn for this first half of chapter 14. So far what we've done is we found the pH of strong acids, we found the pH of strong bases, we determined pH of weak acids, we determined pH of weak bases. Both of those weak bases and acids utilizing a ice table and filling it in with X's. In this last example, we're going to be asked to solve for that equilibrium constant K, which means we're going to have to utilize an ice table, but we get to fill it in with numbers. So that's the good news. No more X's for this type. So let's again just dive right into an example. So initially a weak acid was mixed with water. Once it reached equilibrium, we reached in and measured the pH to be 4.25. Find the Ka value. So let's start with the things that we've been doing, the things that we know how to do. So first, I see this as a weak acid. Let's go ahead and write the balanced chemical equation for this. So in this particular example, they're just using the generic HA for weak acid. And it was mixed with water. Weak, so it is partial. Our acid is an acid, so it's going to be the proton donor. So what's going to be left is just that anion. And then water in this case, again, is our base. It's going to be the proton acceptor. My concentration. It's a proton acceptor, so it's going to be hydronium. It's asking us first to solve for Ka, so let's get that equation on the paper and see if that's going to help us at all. So Ka equals, same thing as it's always been, products over reactants. So we've got our anion, we've got our hydronium, and then for products we've got the weak acid, still not including water because it's a liquid. All right, so we know it's a weak acid problem. We're going to need an ice table, so let's go ahead and make that. And we've got our reactant, product, product. And our initial is going to start the same way that it has. So I'm trying to attach all the things that we've been doing before we talk about what's new. So initially our weak acid. So just like we've always started these, that is going to be this initial value for our weak acid. There is no mention of the products initially, so we're going to assume 0 and 0. All right, so if we are being asked to solve for Ka, that means that we have to put actual numbers into this equation. So I have to have an actual number for the equilibrium concentration of hydronium and for our anion and for our weak acid. So we have to have actual numbers, which means our ice table is going to be filled in. If our ice table is filled in with numbers, we must have at least one of the values at equilibrium. So we have to have one of these numbers. Then we can kind of reverse engineer to fill the rest of the table out with numbers. So how are we going to get one of these values at equilibrium? Well, it tells us once it reached equilibrium, the pH was 4.25. Now, if we only had a way to get from pH to one of these concentrations, can we get from pH to one of these concentrations? Maybe we can use the following formula. Nope, not that formula. Hydronium ion concentration equals 10 to the negative pH. Oh, well, if we only knew pH, we could solve for the hydronium ion concentration at equilibrium. We know pH at equilibrium. So to determine the hydronium ion concentration at equilibrium, we're going to take 10 to the negative 4.25. So hydronium concentration at equilibrium is 10 to the negative 4.25. Oops. And we get 5.62 times 10 to the negative fifth. This is the value for hydronium at equilibrium. Which means we know that the change is 5.62 times 10 to the negative fifth. And we know this change is going to be a positive 5.62 times 10 to the negative fifth. And we know this change is going to be a negative, so if the products go up, reactants must go down. So we know that this is going to be a negative 5.62 times 10 to the negative fifth. Okay. So at equilibrium, this is 5.62 times 10 to the negative fifth. And to solve for this one, I'm going to tell you what I'm plugging into my calculator. I'm going to plug in 0.1 minus this value right here. So 0.1 minus 5.62 times 10 to the negative fifth. And I get a value of 0.999. Now that we have our values at equilibrium, we can take these actual numbers and plug them into the Ka equation. That was the whole purpose. So let's do just that. So Ka equals, we're going to have 5.62 times 10 to the negative fifth times 5.62 times 10 to the negative fifth divided by equilibrium concentration of our weak acid is 0.099. So plug this into our calculator and chug our way through it. So 5.62 times 10 to the negative fifth times 5.62 times 10 to the negative fifth divided by 0.0999, and we get that Ka equals 3.16 times 10 to the negative 8. So to summarize this equation, or this problem, we're asked to solve for Ka, so we must be able to fill in that Ka equation with all numbers, which means we have to fill our ice table in with actual numbers. If we're given the pH, we can determine the hydronium concentration and therefore determine the change, which allows us to fill in this table with numbers. I'll work another example, but that's it for the new material for this chapter that kind of ends the first half of this chapter. I hope you guys found that helpful.